Well, you know this has to be a great lecture because Homer is introducing it, right? All right, section 10.4, the derivative. So let's talk about rates of change, how things change. Your change in distance with respect to time, the change in cost with respect to production. Hey, that's business, right? Change in output with respect to time. So as we can see, this tells you how things might change. So how do you typically find average speed? You went to grandma's house this weekend. What was your average speed? Well, you typically say miles per hour, but what you're giving me is your change in distance over the change in time. And we could look at something like this graphically because your average speed is certainly based on taking a beginning point and an ending point, and of course finding that distance, and then taking the time and divide that, and that gives you average. Well, if you notice, what that is that's the slope. If I find the distance total, so the y2 minus y1 would be my total distance, and then I divided it over the total time, that gives me my average speed, which is simply the formula for the slope. You're used to seeing y2 minus y1 over x2 minus x1. So what we're going to do in this class is we're going to make it look a little bit more nerdy. And instead of saying y2, if you remember when you got to functions, you would say y is a function of x. So that's all we're doing is changing the format here a little bit. So y2 minus y1 is the same thing as f of x2 minus f of x1. Let's look at the difference between an average rate of change and an instantaneous rate of change. So at exactly 8 a.m., how fast were you going? Well, you can't get exactly 8 a.m., right? You can get 8 a.m. in 13 seconds and 14 milliseconds and blah, 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 right? So you can never get an exact value, but what you could do is you could average and say, well, between 7:59 and 8:01, this was my average speed. Or, I mean, you can even do more. You can break it down to seconds, and as I said, even milliseconds. So you can make your time interval here get smaller and smaller until you're finally looking at, but I want to know a speed at any time interval, and I want to get to the point where at an exact time. Oops, went the wrong way. So if we want to determine speed at any second of time, and we'll call this x sub 1, instead of these intervals, what we're going to do is we're going to let my interval here, I want to know at exactly this x sub 1. I don't know, let's say that it's 1 o'clock. Make it easy with the 1. Well, what I do is I find my change in distance over my length in time. So my distance here, as you can see, would be my x2 minus x1, and then evaluating both of these points would be my numerator, my distance. I'm sorry, I think I said my distance was the bottom. Scratch that. The bottom is the actual time interval. Well, what I would like to do is say, what if I let this distance from x1 to whatever this point is, what if I let that equal a distance of h? I just call it h. That's my distance. Well, I could find this distance. How do you find distance? Remember we said x2 minus x1? Well, I could take x sub 1 plus h minus x sub 1, and if you notice, the x sub 1's cancel, and I end up with just an h. So kind of keep watching this little formula here because I've manipulated it. Instead of saying, you know, back here we started with f of x2 minus f of x1, and then I said, well, let's call that second point x sub 1 plus h, because that's how I'd get there with the distance, right? And so if I call x sub 2 that, wherever I saw an x sub 2, I replace it. And then I say, well, if that distance is h, then I can actually replace the denominator, my length of time, with h. And what I'm going to do is I'm going to sit here and say, well, let my intervals get smaller and smaller and smaller and smaller. And so the question is, how small do you make the distance? Well, that kind of matters what you're doing. If you're building a table, can you be, you know, a fourth of a centimeter off? I don't know. The table might wobble. You know, that might be a big deal. But if you're, you know, looking at something very, very precise and you have, you know, very good instruments to measure, could you be off a little, you know, a little bit if you're measuring very precise? Maybe not. And so as you're going to see the distance here, we're going to say that h approaches 0 is what we're going to end up doing, meaning that our distance between in this interval is going to approach 0. It can never equal 0. Why? Things blow up, right? Because if I let h equal 0, I'm dividing by 0, and that's a bad math student. Don't you ever do that, okay? So I know that I'm going to let my interval get small. The question is how small? So what I can do now is I can use this definition for any x. And you can see that it doesn't matter this variable name. I'm just saying at a particular time, an instantaneous rate of change, not an average. I want to get to a point where I can pick any x. Now we're not to the instantaneous yet, we'll get there. And once again, I'm letting my distance approach 0. It's getting smaller and smaller and smaller and smaller, but it can never equal 0. But if you notice, this is still the slope formula. Nothing's changed. Every single calculus book you pick up, it's going to talk about Galileo's free fall law, where Galileo dropped a solid object from rest. So he's up here on top of the Tower of Pisa, and he, with the fall distance proportional to the square of the time it has been falling. So if we let y equal distance fallen in feet after t seconds, Galileo came up with this equation. Not a big deal. Just says if I have a particular time, I can get the distance that an object has fallen. Now you might see this written in this right-hand equation. Like if you go out and Google, I know you guys Google everything, right? When you can't figure out something out, you might find this equation because Galileo, of course not being American, used the metric system, and that's what this is. But they're the same formula. It's just this y will give you distance in feet, and this y will give you distance in meters. So I think the Galileo example is boring, so I've tried to make it a little bit more exciting. You've committed a murder. You scared? You killed me. Why would you kill me? The cops have you surrounded at the top of the towers of America. You nervous? 750 feet up. You drop the murder weapon over the side. What is the average speed the weapon is traveling the first 2 seconds of the fall? Average speed, average rate of change, the change in distance over the change in time. So in other words, if I want to know what the average speed the weapon is traveling the first 2 seconds of the fall, I would start from 0 and go to 2 seconds. So I'd take my average rate of change in feet over the change in seconds. Well, what's my equation I'm dealing with is this Galileo, where y is my feet and t is my time. I went ahead and graphed this because I can see that I'm looking at just averaging. My numerator is the change in my y, so it goes from 0 to 64. And my denominator is the change in x, which is going from 0 to 2. And as you see, I get the 32 feet per second. Putting this in that average rate of change formula says that I go 16t squared minus 16t squared, 2 seconds, 0 seconds, and then the bottom is my interval of my time, 2 minus 0, and you see I get 32 feet per second. Well, what if we changed our mind and said, well, what is the average speed during the 1 second interval between 1 and 2 seconds? Well, I just manipulate my formula a little bit and I get 48 feet per second. Well, what if I want to know between 1.1 and 1? If you notice what I'm doing, I'm trying to get closer and closer to 1. Exactly 1 second. Well, is a tenth my distance, meaning my h being a tenth of a second? Is that small enough? I don't know. You know, it might be if I'm trying to hit the garbage truck with my weapon so it can drive away, right? And so I can continue to say, well, let my interval get smaller. Notice 0.0001. And so where you see the variable, I plugged in my x plus h, or in this case it's t, right? My t plus h, and then my t that I'm interested in, my time of 1, and then the bottom, I went ahead and showed you the interval, but you could just put in 0.01 because that's my h, that's my distance. Well, if I continue to get smaller and smaller, notice what's happening here. It might be easier to see this with some table data. So I want to know at exactly 1 second. Well, I average between 1 and 1.1. Then I average between 1 and 1.01. In other words, this is my interval length. You can see what's happening after I make this my h approach 0. This is approaching a limit value, my speed of 32 feet per second. And that's what we call the limit. So this would suggest that the murder weapon is falling at a speed of 32 feet per second at exactly 1 second. So what we're doing when we're making our intervals smaller and smaller and smaller is we're starting with an average rate of change and we're getting to an instantaneous rate of change. Let's check this algebraically, meaning let's use our change in distance over our change in time. Our equation is 16t squared. Remember, this is our f of x plus h minus f of x. So I plug in my equation, and where I see my variable, I put my variable plus h, and then where I see my variable, I put my variable. Well, I want to know when t is exactly 1 second, so where I see a t, I plug in a 1. And then we get all algebra crazy here and we FOIL this out. So remember, that's 1 plus h times 1 plus h. When you FOIL this, you get 1 plus 2h plus h squared. That algebra is going to come back to haunt you, right? So that's just FOILed. I just multiplied 1 squared is 1, 16 times 1, I get 16. Now I'm going to distribute this 16 to everything inside the parentheses. And notice everything that is not in terms of h will cancel. And so now I have this piece here, which I can factor out an h. My h's can cancel. And then I end up with 32 plus 16h. Aha, I see a 32. We said we are going to let h approach 0. So as h approaches 0, our limit is this 32 feet per second. So the big difference here is average rate of change versus instantaneous rate of change is when we let our limit here, this piece right here, approach 0. We let that interval get smaller and smaller and smaller and smaller, and that's what's happening. So we start out with our secant line. Our secant line is we take an average rate of change, we pick two values, we find the slope, and then what we're doing is we're bringing this point down closer and closer and closer and closer because our distance here we want to be h. So that's what's happening with this little animation right here, is we're bringing this point all the way down till finally we only touch this interested value, like time equals 1 second, in one place. When that happens, that's called a tangent line. So a secant line is our average rate of change. We can get average speed. That gives us the slope of the secant line. The tangent line, the slope of the tangent line, gives me my instantaneous rate of change. Okay, so That's my, for example, instantaneous speed. So we say the instantaneous rate of change of a function f of x at a point x equals a is the limiting value of the average rate of change as the point x equals a plus h approaches x equals a. That's too mathy for me, blah, right? What you're finding is the slope, because remember the slope is a rate of change. You are finding the slope at a particular point on the curve. So that's why we need this whole limit thing. You're letting your h get smaller and smaller and smaller until you're right on that point, and that's the slope of the tangent line. This definition here is the definition of a derivative. So this little prime thing says this is the derivative of my function is found by taking the limit of my change in my y's over my change in my x's. So it's given me my slope of my tangent line. And we also call the derivative velocity, but it's the slope of the tangent line. And that's the important part, is that you understand that you're finding the slope if your limit exists. So to find a derivative, you're finding the slope of the tangent line at a particular value of x. So let's say, for example, I want to find f prime of x. What that means is find the function for the slope, and then I could use it to plug in any value. And so I have this square root of x plus 2. As for x is greater than 0, why does x have to be greater than 0? Because you cannot take the square root of a negative number. You remember that, right? So I go back and I say, well, here's my definition. Everywhere I see an x, I plug in x plus h. So where you see an x, I plugged in x plus h. That's this first piece right here. And then I need my plus 2. Minus where you see an x, I just plug in x. So that's just my original function. If you notice here so nicely, these 2's, 2 minus 2, those are going to cancel. So I end up with this piece. Now, what you do when you find the limits is you check every step. Can I plug in 0? Nope. Can I plug in 0? Nope, because I'll be dividing by 0, right? So I need to be able to do something with this. We learned with limits, typically we look to see if we can factor. Well, I don't see anything I can factor. If you remember something in algebra called conjugates, we use these a lot when you have radicals, and where you see this sign, you rewrite it with the opposite. So this piece, this conjugate, I'm just multiplying by 1, right? The same thing over the same thing is 1. But I'm doing, instead of a minus, I'm doing a plus. So I'm going to FOIL the top, and the bottom I'm just going to pretty much leave it. Now you might say, but what happened to all these square root symbols? When you multiply a square root times a square root, the square root goes away. So that's that x plus h. If you FOILed this, you would see your middle value gets canceled out. And that's the whole point of the conjugate. And then your last value is the square root of x times the square root of x. When you multiply square root times the square root goes away, and I get minus x. I didn't do anything with the bottom, I just put it together. You can see the x's cancel. Now the h's will cancel. Now I'm to the point I can plug in 0, and I can let h approach 0. So if I plug in 0, I get 1 over the square root of x plus the square root of x, or 2, because there's 2 of them there, 1 over 2 square roots of x. So what this is another function. I had an original function, and I wanted to find the derivative of my original function. What is the derivative? If I want to know the slope at, let's say, 4. I want to know for my original function back here, what is the slope, what's the rate of change when x equals 4? Well, I just found my derivative, so I simply plug in 4, and this tells me the slope of my function at x equals 4 is 1 over 4. So in other words, the change in y, 1 over the change in x, 4. The tangent then would be the line through the point 4, 4 with a slope of 1, 4. Do you know where that 4 came from? I always ask students that, because if you see numbers, you know where this 4 came from because that's the one that was given. You know where the 1/4 came from because we just found the slope. This came from my original function. I evaluated my original function at 4. So square root of 4 is 2. 2 plus 2 is 4. So what I do is I write this out in my point slope form. My y minus y1 equals m times x minus x1. My y is 4. My slope is 1/4. And my x is 4. And so now I can find this tangent line by, I can go through the steps. I've just distributed my 1/4 and I've solved this for y. Now, I always say you should understand what you are doing, and how you can understand that is with a graph. I have this purple function, that's my original function. I want to know what the slope of that function is at x equals 4. That's what I found when I found my derivative and I plugged in 4, I got the 1/4. Well, now I want to know the equation of my tangent line, and that's what I found by plugging in my point and my slope. A company's total sales in millions of dollars, t months from now, are given by this function. Find and interpret it, s of 25 and s prime of 25. Use these results to estimate the total sales after 26 months and after 27 months. Well, we can do the first one, because the first one, just evaluate the function, plug in 25. And what does this number mean? 25 months from now, that was my t months, sales will be $7 million. Well, how do we find s prime of 25? That's the derivative. If you look up here, this is the same example that we just finished. The square root of x plus 2, we're just using a t. So I already know what the derivative is. We found that before, 1 over 2 square roots of t. I plug in this value, 25, and I get 0.1. How we interpret this is, remember, this is a slope. So this is the change in my y, which are the change in my sales, over the change in my x, which is the change in the month. So this would say the rate. That's the key, is that the derivative is a rate. I just took the 0.1 million because they said this was in millions, so I multiplied it by a million, and it says 100,000 per month that sales will be increasing 25 months per now. Use these results to estimate the total sales after 26 months and after 27 months. The only problem with this instantaneous rate of change is we're saying nothing changed. Sales didn't change, demand didn't change, rent didn't go up, nothing changed. So what we could do is we could take our month 25, to go to month 26, it would change by this rate. So we could simply take our 7 million plus this 100,000 per month that it's changing and get after month 26, and of course we could do 2 times to get after month 27. Once again, we could look at the graph of this. I can plot that point, the 25, 7. I have a point, I found the slope, and I can go through my y minus y1, and I can actually get my tangent line equation.